Thank you. Thank you, DJ. Where are you, bastard? Sorry. A very excellent talk, DJ. I'm touched. Thank you. To the point that, for example, this introduction about what I've done should be probably the people that I worked with, the privilege to work with you and others. I think we all work with individuals within our work, and that makes us much better, and that makes us to rise to another level. The talk that I'm going to present today is really about the deontology of data science. The purpose that I have is somewhat parallel to what DJ had just mentioned, is that I believe that there's something that's fundamentally missing in our science. It's deontology. And the goal really is about to take the time at this conference, because as DJ said, the time is now to think about it and to have that open dialogue. To make my case, I'll start with the definition of data science. What do we mean by it? Well, DJ and Jeff coined the terms in 2008-ish, roughly, and it was really a master of 5 trades. A data scientist was a great engineer who built the systems that we all depend upon. A data scientist was a machine learner who can understand all these algorithms. A data scientist was that master at creating products from data, would see data and opportunities from it to change people's lives. A data scientist was an individual who could look at data and create a story from it, an insight that's very valuable, and articulate it in plain English for everybody and support it with a nice visualization. And a data scientist was a hacker who could do it very quickly. So a master of 5 trades. William Cleveland, a little bit earlier, just equated data scientists as a technical extension to statistics. And a little bit earlier, Jeff Wu equated data science to just statistics. If you further back, Peter Noor didn't like computer science because in the end, computers manipulate bits and bytes and prefer the term data science. And if you want to be a little bit pedantic, which I am at times, the terms data entered the English vocabulary very, very early on. It's roughly in Shakespearean times, and science much earlier. But all of this tells one thing. The root of our science, on one side, is certainly the mathematics of uncertainty. And that goes back to Blaise Pascal when he's trying to solve the problems of Chevalier de Marais and his dice addiction, starting the thinking about probability, not certainties. Reverend Bayes comes up a little bit later, through the 17th, 18th century, about conditional probabilities, which we all use today. And I can also point out to Carl Gauss, roughly at the end of the 18th century, beginning of the 19th century. But that's a fundamental root of our science. That's one of them. The other root of our science is clearly about computer science. We're leveraging these machines to be much more efficient. And that traces back to roughly last century. Alan Turing, Grace Hopper, who actually had the foresight to say, well, we should not be all coding assembly. Sometimes reading with the English key terms would actually be helpful. And Don Knuth told us to look at the complexity of the algorithms that we're using. So those are the 2 roots of our sciences, and if you look at it, through time it flips back and forth. What DJ and Jeff did was to center it in the middle. That it is a science on one side that's keyed in mathematics, and it is a science on the other side that's keyed in our ability to build these applications. And it goes back and forth. If I can stop a little bit the progress of time, I would go back and say, well, what is the technique that we taught 25 years ago, let's say a quarter of a century ago? Around all the things that we're doing in data science, there's one fundamental technique that, by the way, when we started at LinkedIn with DJ, I used to ask that question. Pick up one method that you're good at, that you really understand, and explain it to me. And there's one thing that people picked up from time to time, and I would not explain it, but linear regression, right? It's very simple. We used to teach it in one full college year. Not 1 hour, not 2 hours, one full college year. If I were to teach you the math behind it, that's probably because you have the background entering the class, maybe a couple of hours. If I teach you how to actually fit the model, that's probably a couple of hours also, because guess what? You have computers to do that. You just enter the data, click go, LM something, and you get the output. But what we taught is really about how to look at the model. What does it really mean? In this case, it's just a naive view of trying to predict GDP in millions of dollars by population size. It's a data set that I quickly assembled from OECD's and mashed up together with the World Bank data. And the country on the right is Brazil, We said a little bit more than 200 million individuals. And what we really thought is, well, sure, you can fit that line. By the way, that methodology was developed by Carl Gauss 190 years before. It didn't change. It was still the same. Same assumption, same everything. Except it was faster to compute. And what we did said, what would happen if you had a point suddenly that's outside of the range of the parameter space? Let's look at the US. And if you look at the US, suddenly your line goes way up. It's tremendously affected by just one single point. Doesn't matter what the other ones were. And now suddenly your prediction, if you had 1 million individuals in your country, your GDP raises by $41 billion. Well, what happened if you put China in it, which is even further out, so far out that it's not even in the picture on the x-axis, and the line goes way down. So we spent 1 year to teach what are the assumptions behind the model. When you look at the model, how does it behave on the different inferential points? How to do feature transformations, et cetera, et cetera. We spent 1 year on that. Not on the technique itself, how to do it, but just 1 year on the application of it. So park this on one side. As I progress in the evolution of our science, I think there's 3 recent accelerators that I certainly would like to point out. The first one is open source. We don't have to reinvent the wheel in everything that we do. We just can pick up components and build up on the work of others. And that didn't exist before, let's say, Richard Stallman was really a big proponent of it. Another one is clearly Hadoop as a compute power. And that originated by work that published by Jeff Dean and others at Google around GFS and MapReduce. And the later one in the recent revolutions is about the graphic GPUs. And the recognition by Jensen at NVIDIA to recognize that we could do more with these graphic chips. But in order to do so, a couple of things need to be done. We need to have that abstraction to code to it, and that's what CUDA is, and to get into that space. And since then, it just took off. And you see where the headlines have been going today. It's about data this, data that, big data, artificial intelligence here, machine learning, software is eating the world, et cetera, et cetera. And it's moving to a place where it's an AI company or an AI world, dominated by this, where the unreasonableness, effectiveness of data and models are transforming everything that we do, from the practices to the things that we've built. And notice from what DJ has said is we're moving away from individuals. The techniques themselves are just enthralling and seems to be great that we play in this wild world. What I'm saying is that it's actually, there's a danger that we've get in the situation that looks like a little bit like a black box, and it's more like a babushka, these Russian dolls with multiple layers. But let's simplify it to a black box. There's within a box, and there's outside of the box. Within the box, you have the data scientist who fits a model, who has data to play with, and there's lots of work to be done to clean up the data and everything. And within that world, you're trying to find the best model. And what do you usually do? Sorry, DJ, I had to put an ROC curve. This is for binary classifier. It's an example from the Microsoft R Tiger Team website. It's about whether you're going to tip a taxi driver or not. And you have different models, and we all have done it. I'm not going to explain the ROC curve. And you pick the model with the biggest area under the curve. Then as a data scientist, you say, well, there's something that I need to fix, a threshold. What threshold? Well, I look at the true positive rate, and I figure the level that I'm okay. And it's usually, let's say, 90%. And very rarely that very nice curve is not available. It's not there. It's really closer to the line because the models that we take or the things that we build tend to be very complex. And you compromise on this line. Either you say, you know what, I get 5% or 30%, et cetera, and you start thinking about where that threshold is. And you fix it. Now that's the model that you're going to use and ship it to production. What is that model going to do? Well, 30% of the time, 40% of the time in this case, for example, if you are not a tipper, I'm classifying you as a tipper, and then 10% of the time, if you're really a tipper, I missed it. There's some mistakes. That's what happens within the box. You come up with your best model, and you've gone to great depth to figure out which one it is. The world outside that box is slightly different. I'm a developer, and this is from iOS ML Core examples. I'm going to code an example to recognize a picture, just to tag it. And these 4 lines of code is really everything that I need to do. I send my picture through a pixel buffer to a model prediction that is going to give me tags back, and I'm going to display it later on. It recognizes that this is a jersey, this is a cat, this is a koala, and makes a mistake on the hot dog or the cheese sandwich. And that's good. That's 3 out of 4. The examples they're real. They're not imaginary. And you might say, what do you mean? But there's something missing, right? I still need a data scientist because that model needs to be done somewhere. Somebody needs to do it. But I'm sitting outside the box. Well, how do I do it? I go to GitHub and I find the model. And a bunch of models, and these are MobileNet from that leverages a TensorFlow Mobile. And you can figure out which model you want. And there's maybe papers behind it that tells you what all these parameters are. But from a developer perspective, what do I look like? And it's interesting here is that the first 2 columns is not about quality of fit. The first 2 columns is about how much power you're going to use per classification and how much data you're going to use, meaning memory. The memory footprint and the power usage of your application, which makes sense because it's going to be on a phone. The problem here is that outside the box, you have no idea what the model is. You don't know whether your picture is in the parameter space. So recall the example of linear regression that I said before. You don't know whether the model that you're using is actually adapted to the case that you're going to actually use it for. It may make mistakes. And if you think that doesn't happen, just remember 2 years ago, the picture of African American from Google Photos that was classified as a gorilla. So it does happen. You make mistakes. And we know it's 30 or 40% depending on where you cut on the ROC curve. So the problem that is happening is that, well, when we operate in this world, we are actually fundamentally forgetting that sometimes there are people on the other side. What we're forgetting is that models don't have all inconsequential cost when they fail. And here's an example that was in the literature just recently about keeping people in jail. The model is built to predict whether you're going to be a recidivist or not. And there's a wide set of models, and you can go to this website to look at a lot of them. The use case is you are in jail, you're a parolee about to come out, and you go to a parole board, for example, and so what is the likelihood for you to come back within a year? And if you look at the collaterals from that software, you have these nice curves that says, well, if you use our score, as you go up, the score goes up, the likelihood for me to predict that you're going to be a recidivist goes up. My model works. And if you stop here, you say, well, great, yeah, of course it seems to be working, because if you are in the roughly 30s, your likelihood of recidivism is about 60, 70%. Great. You should use it as a decision function whether you're going to keep somebody in jail or not. The problem here is, last time I checked, our judicial system is not about keeping me in jail because the average of me is about to be a recidivist. It's whether I'm committing a crime, not the average of me. I may have a score of 35. It doesn't mean that I will come back. It means that you believe in the Bayesian interpretation that there's a 60% likelihood that I will. A year down the road, I am or I am not. So the problem is that we forgot that these costs are not inconsequential. The danger is that then we actually portray that this is data-driven decisions from valid models. Like if you go back to Combus, which is another software in there, within the collateral, it actually says, yes, we're going to compute risk, and it says, really, you can make defensible solutions. Just use our score, defend your decision on our score, and it's fine. You kept somebody in jail that should not have been kept in jail because our score told you so. Don't worry about it, we got this. So what's really missing is a deontology. How do we think about the ethics of what we do? How do we put them in place? Because the cost of a mistake is not necessarily inconsequential. We're empowering individuals' lives. So let's think about how we actually react from an ethical perspective. What is it that we should be doing? And for this, to start the discussion within this conference, I suggest to piggyback on a framework that Luciano Floridi from Oxford suggested. Look at first at the data, the ethics of data. It's great that we can mash data together, but what is it that you're doing to preserve the privacy of an individual within it? that you mash the data together for the purpose that you thought you were supposed to be doing, and not for something else. Here, Europe is very far ahead of the US, as you all know if you're in this industry, with the rise of GDPR as a rule that we need to all comply by May 25th, 2018. Once you reason in the space that the data is also to be made available to whoever you're going to target, quote unquote, that they have a right to look into it and adjust if there's some mistakes, there's got to be some transparency there. The next one is the ethics on algorithms. We fit models. There are losses, there are gains here or there. Models have biases. How are you transparent about it? How are you going to hold yourself accountable to it? I've been sitting around in a lot of discussions and say, well, in a deep net, it's almost impossible. And you get the feeling that we just give up. We're not going to do it. It's too hard. Well, if that happens, then it becomes that black box. And you go to jail and you don't know why. And you can't even diagnose why. You just kept me in jail. Well, I don't know. The machine said so. Sort of like when you go to the airport in the old days and you said, but I have a reservation. And the person on the other side said, well, sorry, we don't have it. And said, but I need to go home for Christmas. Sorry, you don't have it. And said, but I have the proof. I paid for it. But it's not there. The computer doesn't let me do it. No, we need to be held accountable for this because we are the ones that build it. We are the ones that understand what a model is good or not, what are the model diagnostics in place. So we need to put that into the systems that we build. And the third one is the ethics of the practice. How should we hold ourselves accountable to? I work for a company that has a certain vision and a mission, but I should also hold myself accountable to, so that I feel comfortable that every day when I go home, I think I did good. Because the things that we're building have tremendous impact. And as DJ showed, it will have an impact through all individuals' life. And that's great, because a lot of the things that we do is such a positiveness. But if you tweak it a little bit, it could also go the other way. So how are we going to hold ourselves accountable for that? So think about these three dimensions: the ethics of data, the ethics of algorithms, and the ethics of the practice. And to conclude, I would say, well, the best way to predict the future is to really invent it. So the best way to think about the ethics of this deontology for data science is to actually think about it and to invent it, to put it down, and to build upon maybe the pledge that DJ has shown, and to construct it. And that depends on us. We are the ones that can do it because we understand both sides, in and out of the box. Thank you.